Hello everyone, can you hear me?
Hello, teacher. Yes, we can hear you.
Okay, welcome to this lecture of numerical analysis. Okay,
Thank you. Thank you.
I'm your teacher, Professor Yang, and so totally we have uh, 32 hours for this lecture. Okay, and that will during about 8 weeks. So firstly, I want to tell you how can you get the score of this lecture of this course. Maybe I sh I show you my whiteboard. You can see that. So
Yes, teacher.
at the end, we will not have examination because of this pandemic of COVID. Okay, so then how can we get the score? You will have 2 times of homework. So homework one, you if you finish that, the full score is 25 points. Okay, and also you have the second time, also 25 points, and finally you will write a report, the final report, that is 50 points. So all of this is the 4 points, and together it's 100 points. Okay, so that is how you can get the score. But so in a WeChat group, there is my assistant of this lecture. His name is John. Okay, so he will help me uh, to get your homework or report. So every time you should submit your homework or report to her. Okay, understand? Clear?
Yes, yes,
Okay, okay.
yes, teacher.
Okay, so don't worry. The first homework maybe I will give you after 3 weeks. Okay, so from now on, with 3 weeks, approximate 3 weeks, I will give you first homework. Okay, then the second homework maybe after 6 weeks or 7 weeks. Okay, and the
Yeah, yeah.
final report is after the finish of the all our lecture. Okay, so that is the planning of the for our course, the evaluation of our course. So now I will go back to my lecture.
Okay. Thank you.
So I changed to full screen. So I hope you can see clearly.
Yes,
So
yes, Professor.
so this is
Yes,
the
teacher.
okay. You can turn off your microphone now because I will give my lecture, and of course, if you have question, you can turn on your microphone. Okay.
Okay.
So I have shared my all my slides in the disk uh, the disk of HIT. Okay. So you can download it if you are outside of China. You can use the VPN. Okay. I hope you already get all of these slides. We have totally 6 chapters. And if we have enough time, I can give all of the. We can talk about all of these 6 chapters. Okay. So the first chapter is about the introduction for numerical analysis. Here I give you 2 reference. So if you can able to find them, that's all right. If you cannot find them, that doesn't matter. You just need to follow my lecture. That is okay. Of course, you can find many other books about the numerical analysis. The principle of all these the principle of all these books are the same. So any of the book of numerical analysis is okay. Okay. So one more word is that my lecture, maybe some of you have already learned about the numerical analysis when you were in bachelor. Okay. So um, almost most of the part of this lecture maybe very similar to what you have learned in your bachelor. Okay, that is possible. Okay, but as I know, not of all, not of all of you have learned this lecture. Okay. So let's begin with the definition. What is the numerical analysis? It is the study of algorithms that use numerical approximation for the problems of mathematical analysis. So that means we have the mathematical problems, and sometimes it is not easy to find its explicit solution. So that's why we will to use some numerical method to find approximated solution to this mathematical problem. That is the definition. Okay. So more precisely, we will see the second part is for some motivations. The first one, as I write here, the experimental studies is very expensive. So we developed mathematical models, and since some mathematical model is also very complicated, to find its explicit solution is not trivial. So we need to use the numerical analysis to help us. Okay. So the second, to find the solution of the model. As I said, the explicit solution is not exist. Some explicit solution may not exist, or sometimes they exist but not appropriate for practice use. So here I want to give more details about the second term. Okay. So let's see. I change to whiteboard. Okay. Let's see how to get another page. Wait a minute. I'll change to another page. Okay, maybe I can erase all of them. Okay. So you see, I will give my first example. That is when you when we want to find fx equal to 0, if the fx is a polynomial of degree 2, that is a times x squared plus b times x plus c. This is a polynomial of degree 2. Then to find the solution of fx equal to 0, we know there is a rule, that is the solution is minus b plus minus square root of b squared minus 4 times ac over 2a. Okay, this is a well-known formula for polynomial of degree 2. However, imagine that fx is what is a0 plus a1 times x plus a2 x squared plus a3 times x cubed plus a4 times x power 4 plus a5 times x power 5. Okay, so now what is the solution I for I equal to 1 to 5? So what is the solution of this one? Such that fx equal to 0. So what's the solution for this equation? Do we have a solution for this? So general answer is no, we don't have a solution for such a problem. Okay, so now let's see the second example. So in the second example, I want to say, for sometimes maybe we have maybe we can get we can find a way to find the solution for a mathematical problem. So let's see, we have a linear system like a times x equal to b. So A is a square matrix, A is a vector, and B is the vector. So we also call it the second member of the linear system. So the objective is find the A. Then how to solve this linear system? One way is use the Cramer's rule. Okay, so in that case, so if x can be write as x1 until xn, okay, it's a vector. So for each component, we can find that this is just equal to determinant of ai power determinant of a. So this I is from 1 to n. Okay, this is the Cramer's rule to find the solution of linear system. So this is something we have seen in the first year of your bachelor. Okay, so this is a very famous result, and in this result you see that we need to compute the determinant of many metrics. You see, in a determinant, in a denominator in here, the determinant of A is determinant of A. So this time you need to compute this one. Okay, so let's see the complexity. The complexity means that how many basic operator you need. That means the basic operator means addition, substitution, division, and multiplication. So you see that the complexity to compute this one, complexity to find the determinant of A is capital O n cube. Okay, this is complexity to compute the determinant of A. And then in a numerator of the fraction, you see here that is determinant of AI. AI is also a matrix. So the complexity to find that this is also the capital O n cube. So from this you can imagine that this I is from 1 to n. Then that means you have almost n times this one. So imagine that you need to consider this n very large. So the complexity to find this x is very huge. Okay, it is too costly. Okay, so that means your computer may not able to find the solution with the Cramer's rule. Okay, so in this sense, the Cramer's rule is very important since it gives our the theoretical way to find a solution, but in practice it is useless. Okay, nobody to use the Cramer's rule to find the solution of linear system. So later in chapter 4, we will give you many ways to find the solution of this linear system. Okay, so let's go back to my slide. That is just see that's here. Okay. The third point that means we need to propose approximate solution, and that one should be computed by a computer. Okay, so here maybe I want to give you one more example. So in this example, you will see for some of algorithm, it seems that it is correct. Okay, very suitable for compute. But when you practice it in your computer, you will find very large errors. Okay, so I will first give you such an example, then later I will show you some numerical result. Okay, so such an example is okay. So you see. So you see here, this, sorry. our third example. So I want to find the integral of a function, which is noticed like here. So you will see I want to find the sorry, my pen is not working. So I want to find such a problem. Okay, I want to find such a problem. The denominator is 10 plus x. Okay. So you will see this integration for this function. Okay, and then of course this result depends on the choice of this number n. Okay, so my purpose is to want to find the I20 is what? What is the value of I20? Okay. So then how to find this? I can find a way like, you see, I give you a way to find this. Okay, you see, sorry, there is a mistake. Okay, so I get in plus 10 times in minus 1. Okay, so here, this one just like a definition for in. So can substitute by its definition. You will get and also the second part. Okay, so I make some simplification. Then I will get in minus 1 times 10 plus x over 10 plus x dx. So you will see in the numerator you will have 10 plus x. In the denominator is also 10 plus x. So this one can be cancelled by this one. And finally, you get this. Okay? And this is nothing but 1 over n. Okay? This is nothing but 1 over n. So finally, you get in is equal to 1 over n minus 10 times in minus 1. So what does this mean? This means when you have in minus 1, you can use this this formulation, you can find in. So extra, you can use the iterations to find the I20. So that means you can find the I0. I0 is very simple. You can see I0 is nothing but this one. And this is ln of 11 over 10. Okay, so that means you have an initial value, then you substitute this initial value to here, you get I1, then you put again I1 to here, you get I2 and etc. So this is just a recursive formulation, and you will get a sequence as I0, I1, N2, I19, and then I20. So this is a sequence. Okay, you will get this one. Okay, let's see. This is really a way to find the value of I-20, and I want to emphasize that the computational cost of this problem is not very large, since you have just one division, one substitution, and one multiplication. So that is 3 basic operation. Okay, so the computational cost is okay, and you just need to compute it 20 times. Okay, so let's see. In each iteration, you have 3 operations. Okay, you have 3 operations. Then you have to iterate it 20 times. So finally, you get just 30 operations. 30 operations is not very large. Okay, it's okay. So it seems that this is a perfect algorithm. Okay. However, in the practice, we will see that this is a useless algorithm, since that it introduces a very huge error, and finally you cannot get a very accurate result as we expected. Okay, so later we will go back to my slides. We will go back to this example and show you the reason why this algorithm does not work. Okay, so let's go back to my slides again. Okay, so the third point I want to emphasize that when you develop efficient algorithm, you should consider 2 points in your mind. The first one is to the convergence and stability of numerical method. The second one is the computational cost. Okay, so I think these 2 points are not difficult to understand. The first one means that the convergence and stability of the numerical method means that your numerical solution, this is some approximation of the real solution. We want this solution can very close to the exact solution. In that case, we can say that our numerical method converged and stable. Okay. The second thing is the computational cost. It is also easy to understand. That means we need some algorithm not very expensive to calculate. Imagine that you need to compute something, but the computational cost is too large, so you need to compute it too long. Okay, but for some problem, we need to get the result immediately. Okay, so if your computational time is too long, then even though you get some method that converts, but you cannot get the result very quickly, then your algorithm is also useless. Okay, so you see from this page, we see the definition, motivation, and efficiency of the algorithm in our numerical analysis. Okay, so the first chapter is divided in 4 parts. The first one is the error analysis. The second is the representation of a real number in computer. So here we should understand how we store, how we represent a number in our computer. This is also very important. The third one is the conditioning stability and the complexity of algorithm. The first one is some tips in numerical analysis. Okay, this part we will learn some very useful technique to avoid to introduce numerical errors. So let's start from the first one. So what is the sources of the error? The error they may come from 4 different parts. The first part is the error comes from the model. Okay, you can I give you an example. So here maybe I can write it directly here. So if you get some data, okay, you get some data here. Okay, this is some data. And you want to find the feature of this data. So sometimes you want to describe the feature of this data with some functions. So in this case, you will find that this data is very similar to the value around this line. Okay, just like this line, and this is very similar to exponential of x. So in this case, we make a model. Okay, this function is just like some model. So we say fx is like the exponential of x is like a model, and we use this model to describe some data like here. So do we have some error from this model? Maybe, of course, since we use a model to describe something, and this model cannot exactly coincide with all this data. So in this sense, it is just an approximation. Okay, when this is an approximation, of course, we will introduce the error, and this error we call it the the modeling error. Okay, so the first one is from the mathematical modeling. The second error comes from the data. So that means when you find a way to get this data, okay, you use a way of measurement, okay, and when you make the measurement, you may get the error, okay. So sometimes this is something we cannot avoid, okay. So that means this is something from the sense of numerical analysis. This is something we cannot avoid. The third part is the truncation error. This is something arising from the replace the how to say, this something we want to approximate our mathematical problem by some numerical way. And in this case, you may also introduce some errors. So here I give you an example. So in the first part, you see we use the exponential function exponential x to approximate this data. And then we want to know what's the value of the exponential x. Okay, how to find the value of this one? If we know the value of x, and what's the value of exponential x? So here I don't want to use your computer to find this. Whether we have the other way to find this, the answer is yes, we may find the other way to find the exponential of x. We can use the Taylor expansion. So you can know that you can find that we may have the x power n over I factorial. Okay, so we may have this Taylor expansion. So in this sense, we can find the value of exponential of x by using this formulation. So from this formulation, we just need to make the addition multiplication, since the power is just like a many multiplication and a division. Okay. However, the only question from here is that the index I from 1 to infinity, and we cannot to make some calculation to infinity. Okay, so from this sense, we should make some truncation. Okay, we should make some truncation. That is, we will not make the summation from 1 to infinity. Instead, we will truncate it to a capital N. Okay, we will truncate it to a capital N. So that means we stop here. We stop from here. Then from distance, you will see that if we notice this one, that's fx, so the real number is exponential x minus its approximation fx, you will get an arrow. This is for the index I from n plus 1 to infinity. Okay, so this is our arrow, and this arrow we call it truncation arrow. Okay. Okay, and the last one, we call it the round-off arrow. This is arising from the limitation of our computer. So later we will see a very interesting phenomenon. That is, when you make 1 plus 10 minus 16 in your computer, then if you try this in your computer, maybe you can use the language C or Python to compute it, and finally you will get this is just equal to 1. Okay, how to explain or how to give an explanation of this one? So the reason is that this number is too small, okay, compared to A. So when you make the addition, okay, we do not have enough the figures to restore all these figures. So we should make the round off, and so So that in that sense, this 10 minus 16 is dropped away. So we only have the 1. Okay, of course, later we will continue. I will I will give more details about how we get this one. Okay, so this is the source of error. Okay, so wait. Okay. So now, how to measure error? The first way is called to use the absolute error and absolute error bound. So here I give you the definition. Is here the absolute error. You see, it is just equal to the difference between x minus x star, and also you need to add the absolute operator. So you get the absolute error. This is something as we know before, okay? And moreover, since x is usually unknown, okay, this is something unknown. So to find the exact value of the absolute error is not possible. And instead, we can find some bound, like denoted as delta x star. We just want the absolute error can be controlled by this bound as delta x star. So we get an example that is x equal to pi. The pi is this value, okay, with many figures, okay, infinity figures. And x star is something we use to approximate this pi. So we just make a truncation to here. Okay, we make a truncation to here, and then we drop all the figures after 9. Then what is the error? Of course, Ex is equal to x minus x star. Okay. Then this one is more than 0.5 times 10 minus 5. Okay. So you see, this one is something like the absolute error bound. Okay. This is something we can find by ourselves. From this one, we can find very easily. We do not have a unique absolute error bound. So why I say that? You see that the error, the exact absolute error is 0.0005026 and extra. Of course, it is more than 0.5 times 10 minus 5. Okay, but you will see this is also smaller than 1. Am I correct? Yes, of course. This value is smaller than 1. So from the definition of the absolute error bound, we see that 1 is also a absolute error bound. This is correct. But the problem is that 1 is not appropriate absolute error bound, because we want the absolute error bound control the absolute error, but don't far away from this absolute error. You see, compared to the real absolute error, 1 is too large compared to this one. and instead the 0.5 times 10 minus 5 is very close to this one. So that means compared to this one and 1, of course, this one is better. Okay? So uh, sometimes just the absolute error bound, absolute error, and absolute error bound is not enough. This is because sometimes the background of a value is also important. An example is that when you want to measure the surface of a desktop, uh, uh, sorry, when you want to measure the surface of your desk, or you want to measure all the area of your room. So if the absolute error of these two measurements is the same, imagine that is just 1 centimeter square. Okay. So from distance, you can say they have the same absolute error. And then which measurement is better? So we can easily to say that the measurement for your room is better, since your room is so large compared to your desk, and then you get the same error. That is not a easy task. So you can say that my second attempt to find the area of my room is better. Okay. This is a good example. You will find that the background of the measurement is also important. You should also consider it in sometimes. So here you see this is my second way is called to use the relative error and a relative error bound. The definition is right here. We use the notation ER x star. This is defined as x minus x star absolute over absolute of x. Okay. Sometimes we also use the second definition that is x minus x star absolute over absolute of x star. So you see that only difference is that in the first one the denominator is absolute of x. The second is denominator is the absolute of x star. So use any of these two definitions, okay. And look at compared to the absolute error, you will find here the denominator, the numerator for the relative error is just the absolute error, and we just divide it by its background, that is the absolute error of x. Okay, so that's why we just use almost the same notation, but substitute but add r here. Okay, r means the relative. Okay, of course we may face the same problem here, that is we do not know the exact value of x, so we need to find relative error bound. that is something denoted as delta R X star. Okay, so that is we want to find some value very close to the relative error and which can control this one. Okay, that means this relative error is bounded just by the delta R X star by the relative error bound. Okay, again we pick the same example before, that is x equal to pi and x star is equal to this one. Okay, this is same as before. Now when you compute the relative error, you just use this definition, and this one you can find that it is smaller than this value. Okay, so this value is larger than the relative error and very close to this one. So that means this can be a good approximation of the relative error bound. Okay, once again you will find that the relative error bound is not unique. So our task is to find a bound as close to as the real error. Okay, if this is can be found, you find a good approximation. Okay, so let's make a break. Okay, everyone, let's continue. So you will in this slide you will find that this is a third way to give you an error. This is by a significant figure. Okay, so let's see the definition. Let x be a exact value and x star be an approximation. And suppose that x star can be write in this formulation, that is plus minus of 10 power k times 0.A1, A2 until an and x star. So you see here, you have many figures. Okay, all of these figure, that is A1, A2, x star can be chosen from 0 to 9. Okay, one exception is that A1 cannot be equal to 0. Okay, this is only one exception. Okay, so if we have this condition, that is x minus x star is more than 1/2 times 10 power k minus n. Okay, so if you have this condition, then we can say that x star has n significant figures. Okay, so this is the definition of the significant figures. And simply to say that is that if one number have more figures, more significant figures, that means this approximation is more accurate. Okay, if this number approximation x star has very few significant figures, that means this is not very accurate. So in this sense, by using significant figure, we can find whether a number is accurate or not. Okay, in other words, its error is large or not. Okay, so you see from this definition, we see the left hand side is nothing but the absolute error. Okay, and the right hand side is nothing but absolute error bound. And in this absolute error bound, we can find the n is the number of significant figure. Okay, so let's see an example. That is x is equal to pi, and x star is also equal to this one, and we can find its error. Its absolute error is equal to this one. Okay, and we find that this is more than 0.5 times 10 minus 5. Okay, so you see the right hand side, at the right hand side of this inequality, okay, is this one. If we can, I will give you some notes. So you see here, if I can reformulate it as 1/2 times 10 power 1 minus 6. Okay, why I need to write this one? Since you see in the definition of the significant figures, I need to write like this one, and here the k is the power for the x star. So that means you see x star is, I can write like 0.314159, okay, times 10 power 1. Okay, if I write my star in this form, it is just like the standard formula of the approximation. Okay, so this is the part of the power, and this is the part of the friction. It's like here. Okay, so that means in this example, the k is equal to 1. Okay, the number k is equal to 1. So that's why when I reformulated the 10 minus 5, I write it like 10 power 1 minus 6, and this part is nothing but k 10 power k minus n, and k is 1, n is 6. So x star has 6 significant figures. That is how we solve it. Here I want to give you one more example. Okay, I give you one more example. So in this example, let's consider. Wait. So in this example, let's see z is equal to exponential minus 5. Okay, this is approximately equal to 0.06 6 7 6 7 3 7 9. Okay, and its approximation we denoted as z star is equal to 0.00673. Okay, so the question is how many significant figures do we have? The number of the significant figure do we have? Okay, so here I want to give you 2 minutes to think about this question, and then I will give you the correction. So you try yourself. Try yourself now. Okay, so let's wait. So I will tell you the answer is 2. Okay, it has only 2 significant figures for Z star. The number Z star have only 2 significant figures. So I tell you why it has only 2 significant figures. So the first thing, you should write Z star in a standard form. That is 10 power minus 2 times 0.673. Okay, this is the standard form. Then we should we should write E G star. So this is the absolute error. That is Z minus G star. Okay. So this is nothing but this one. 0.00079 and X star. Okay, this is the absolute error. So we will find we will try to use the definition that is to find whether this is something is more than 1/2 times 10 minus k minus n. Okay, then n is the number of significant figure. So from this standard form of this star, we know already that k is minus 2. Okay, k is already minus 2. So how can I get a number that is larger to this one? Okay, so we can find that this is more than 0.00005. Okay, so this number is more than 0.00005. Okay, and and what's this? This is just equal to 0.5 times 10 minus 4. Okay, 10 minus 4. And this is also equal to 1/2 times 10 power minus 2 minus 2. Since you know that k is equal to minus 2, so n is nothing but equal to 2. Okay, so we know k minus n equal to minus 4, and since k is equal to minus 2, so that implies that n equal to 2. So we only have two significant figures, and these significant figures is nothing but the 6 and the 7. Okay, so 3 is not a significant figure. So this is significant figure. This is significant figure. 3 is not the significant figure. Okay, clear for everyone?
Yes, teacher.
Yes, sir.
So go back to the slide. Here, I have a theorem. In this theorem, I have two consequences. The first one is if x star has n significant figures, then the relative error is more than 1 over 2 times a1 times 10 power n minus n. Okay, this is my first consequence. And the second one is if I know the relative error is more than this this bound. Okay, so that means I have a bound for this relative error. Then I can give a conclusion that is that my x star, this approximation, had at least n significant figures. Okay, so I want to prove it. Okay, I want to prove this consequence, these two consequences, since the proof is not very difficult. So I will go back to the whiteboard to prove these two consequences. So for the first one, sorry. For the first one, we see that wait a minute. So I want to repeat what we have. Sorry. So what do we? If n has n significant figures, then I have a bound for the relative error. Okay. So you see, what I want to prove is that the relative error for x star is more than 1 over 2 times a1 times 10 power 1 minus n. Okay, is that? Yes. So how to prove this one? So we begin from the left hand side. From the definition of this one. Okay, this is the definition of the relative error is x minus x star over x star. Okay, this is the definition of this one. Okay, and on the other hand, we know that x star has n significant figures. So from the definition of the significant figures, we know that this is the definition of significant figure is this absolute error should be smaller than 1 over 2 times 10 power k minus n. So if this relative error verified this inequality, we say that n has x star has n significant figures. So now let's compare to the definition of the relative error and the definition of the significant figures. We find that the difference is that we should make a division here. So that you can just divide this one by this. Okay. So of course, get this. Okay. This is the definition of the relative error. Okay. Then you want to find a number to control this error. Okay, this relative error. So that means we can make some we can change a little in the denominator. Okay, so we want to find a value smaller than this one, and this is very easy to do. That is, you just substitute the x star by 0.81 times 10 power k. Okay, so let's recall that x star can be write as x star can be write as 0.81 into an x star times 10 power k. Okay, 10 power k. So of course this is larger than 0.81. So maybe it's better to add the absolute. Okay. So this is smaller than 0.81 times 10 power k. Okay, so that means for this part you just dropped all the figures after a1. So of course you get this one larger than this one. So now you have this one, and then you find this is nothing but 1 over 2 times a1 times 10 power 1 minus n. Okay, this is exactly what we want to prove. So we prove it. Okay, so this is for the first consequence. So let's see the second consequence. The second consequence we start from you see we start from inequality. Okay, so we start from the relative error, which is smaller than which is smaller than 1 over 2 times a1 plus 1 times 10 power 1 minus n. Okay, this is the condition we have, and then we want to find how many significant figures we have for x star if x star verify this inequality. So again, you see we start from the left hand side. This is the relative error of this one. That is, the definition is x minus x star over the absolute error of x star. Okay, so we know that this is more than this value. So you can see we can multiply x star to the right hand side. So you get x minus x star smaller than x star over a1 plus 1 times 10 minus 10 power n minus 1. 10 power 1 minus n. Okay. So you see here, now this time the x star is in the numerator, so we can find a value to control this one. So to control this one, you just need to find a1 plus 1 times 10 power k over this one. I think this is clear since x star in absolute is equal to 0.81, a2, and x star times 10 power k. So of course this is smaller than 0.81 plus 1 times 10 power k. So that's why we get this one. And then if you compute it, it is nothing but 1 over 2 times 10 power 1 minus n. So that means we have n significant figures, okay? And we had at least n significant figures since in this step, we find a large number to control this one. So so in this part, some figures may be lost when you use this technique. Okay, so let's go back to the slide. Okay, we successfully proved this theorem. Okay, you may see this is not difficult to prove. Okay, let's continue. So the second part is to represent a real number in a computer. So how can we represent a real number in a computer? In a computer, we write a number with the basis b. So a real number x can be represented under the form of x equal to plus minus m times b power e. And the b, as I said, this is the basis, should be larger or equal to 2. The number m is called the fraction, which is defined as m1 times b minus 1, m2 times b minus 2, and x star. So here mi can be chosen from 0, 1 until b minus 1. Okay. So of course here this m1 cannot be equal to 0. Okay, this is only exception. And then the e we call the exponent. Okay, this exponent can be equal to e0 times b0 plus e1 times b1 plus until x minus 1 times bx minus 1. Okay, so this s is an integer. Okay, so since our computer has finite memory, so the fraction is stored by the first R number. Okay, so as you see, we should make a truncation for the fraction, since we can only represent a number with the finite figures. Okay, here is a very useful example. We call it the standard IEEE 754 1985. So this is in the year of 1985. We give the such a standard, and until now we still use such a standard in our computer. So with this standard to represent a float number precision, okay, so that is usually we call the 64 bits. Okay, so we may, so maybe all of you have used the Windows system, and your Windows system is 64 bits. Okay, so here in this standard, this special standard, the basis is chosen as equal to 2. Okay, so in this standard with 64 bits, how we present a real number? It is divided in 3 parts. The first one is the sign, and the second is exponent, and the last one is the fraction. Okay, so very easy to understand. The sign means plus or minus. Okay, so in this just 1 bit, we can choose from 0 or 1. Okay, so 0 represent plus. Okay, 1 means minus. Okay, this gives the sign of a real number. Then we see we have 52 bits to represent this fraction. Okay, this fraction is written like here. So m is equal to 2 minus 1 plus m2 times 2 minus 2, and until m53 times 2 minus 53. Okay, as you see, when we look carefully here, for this m, we only have m2 to m53. Okay, we don't have m1, since m1 should be always equal to 1. Okay, so we only need m2 to m53. So each mi can be chosen from only 0 and 1. So we have 52 bits. Then the exponent, we have 11 bits. Okay, and you will see e is equal to e0 times e0 times 2 power 0 plus e1 times 2 power 1, and x dot until e10 times 2 power 10. minus 1022. Okay. So each of EI can be chosen from 0 or 1, including the first one. Okay. So by using this formulation, we can find our E is just between minus 1021 to 1024. Okay, and then there's two very special value, that is when E equal to minus 1022. Then we use this number to represent 0. Okay. Another exception is E equal to 1025. When E equal to this one, we use this one to represent infinity. So with this representation of the real number, we can construct a set of number in this standard IEEE. We denote it by the capital F. Now we have the question is maybe we can say this is two exercise. The first exercise to compute the largest number of the F, that is X maximum. Okay, so go back to here. How can we find the largest number in this set F? So I tell you the answer. This is easy. That is, you just take the maximal value of M and the maximal value of E. Okay, for the maximum value of M, you see in this number. Only what you can choose is for just MI, and I can only choose from 0 and 1. You see, you can only choose MI from 0 and 1. So to find the maximum value, you just need to substitute all MI by 1. Okay, and then of course for the exponent part, you do the same thing. Since you can choose freely by yourself all the value of EI. Okay, so you just substitute all EI by 1. Okay, so in this case, you get your maximum value. So you from here you can see your maximum value of E can just be equal to 1025. Okay, and times this M. So maybe I should write to you. So for this one, for the largest value, okay, that is X maximum is equal to 2 power 1025 times times 2 minus 1 plus 2 minus 2 until 2 minus 33, and this is the largest number in this set F, and this approximately equal to 10 power 308. So this is the largest number we can represent in the IEEE standard. Okay, then what is the smallest positive number of F? Okay, so So you see, for the smallest positive number, you just need to when you choose the value of m, you just need to choose all mi equal to 0. Okay, so all these terms cancelled. And of course, for the exponent part, you just need to take the smallest value, that is minus 1021. Okay, so in this sense, you see the smallest positive number we denoted x pose mean is just equal to 2 power minus 1021 times 2 minus 1, and this is approximately equal to 10 minus 308. Okay, so this is the largest number, and this smallest positive number. So you can only represent your value between this one and this one, and the value smaller than this value will be considered as 0 in computer, and the value largest than this one will be considered as the infinity in your computer. Okay, so the second exercise, you see, we propose the two algorithms to determine a numerical approximation of x maximum of x post mean. So here I propose you can use your C language or your Python to program a code to find these two values. Okay, so maybe you can try yourself. So thanks to the represent. I hope you understand how we represent a real number in your computer. Now, thanks to the definition of the IEEE standard, you can see when a number have more figures when a real number have more figures, like here, you see, you just need to firstly write your x in such a form with this m is equal to this one, and okay, remember that the m is right in the basis of 2, so for each number can only be chosen from 0 and 1. Okay, so here you see this subscript means the basis of 2. Okay, and then if this friction m have more number than m53, so that means it has figures as m54. Okay, so here we should make some random step. So how we make it? You just need to analyze its figure m54. So if m54 equal to 0, okay, you just dropped all the figure before m53. Okay, if your figure is equal to m54, if your figure of m54 if you figure m54 is equal to 1, okay, is equal to 1, so we should add 1 to m53. Okay, we should add 1 to this one, so you get this number. Okay, this is called the round-off step, and in your computer, it just do the calculation like this. Okay, so you see, the absolute round-off error is just like here. Okay, so the x is the exact value, and this is the value after the round-off step, and this error will be always smaller than one half times 2 minus 53 times this power. You can see the power is always be the same. Okay. Okay, then you can compute the relative round-off error is equal to this one divided by x itself. So by using this formulation, then we divide by this one, and then this is more than 2 power minus 53, and this is approximately equal to 10 minus 16. Okay, so in our computer, the relative error is approximately equal to this one, and this can be explained that what I have said, that 1 plus 10 minus 16 is equal to 1. Since this number is too small compared to 1, so this one can be considered as the round-off error, and this round-off error will be dropped away. So finally, you just get 1. Okay. Okay. So here I have one more exercise, that is compute the smallest number of such that x plus 0.5, when you make the round-off error, should be larger than 0.5. Okay, then you program it with your algorithm. Okay, so maybe it's almost the end of for today. I will leave you this exercise. You can try yourself, and Thursday morning, I can give you the answer for this question. Okay, so we stop here for today. Thanks for your attention.